So good morning, everyone. So this is the third day of the school, and Professor Amar Vutha from University of Toronto, he is continuing. This is his second lecture, and there will be one more. So Amar, over to you.
Okay, thank you very much. Again, good morning, everyone. It's the same day for me as it was when I last spoke to you, but I hope you've had some time to digest some of the things that we talked about yesterday for you. We'll continue this today, and today what I thought is I'd tell you a little bit about how we use atoms and molecules. Yesterday, you saw a bit about why. And so I decided to focus on a slightly different question today. And so we'll see some of the actual mechanics of how these things get used. Once again, just a reminder of the things I told you yesterday. Again, please feel free to treat this like a lecture. So feel free to interrupt. I'm happy to entertain questions. I don't have any agenda or specific endpoints I want to reach. And so please feel free to stop me. If you have any questions, we can do this in a way that makes sense to everyone. And again, if there are people who are joining us today who were not here yesterday, I've pitched these at the level of a starting graduate student. And so to the super experts in the audience, I apologize, especially in today's presentation or today's discussion, there will be some topics which you may have seen at a much more formal and or higher level in other lectures in this series so far. But I will try and give you a sort of experimentalist view of some of these things, and I hope you find them interesting. All right, so this is what happened last time. Last time we talked about how atoms and molecules have nice symmetries, right? They obey these C, P, T, and Poincare symmetries. And so because of that, we get conservation laws. Because of that, we get selection rules, all of which can be broken slightly if there's new physics. And the second thing we saw is that even though atoms are electron volt scale objects, and we're talking about physics happening at hundreds of tera electron volts, despite that energy difference, because of the extreme high precision that you can get with atoms and molecules, it's not really a problem. In fact, it can be quite sensitive to extreme high energy physics that's well beyond what you can reach with colliders. And so today, what we'll do is build up some of the details of how precision measurement techniques work. People spend their entire lives working on this kind of thing, and so obviously I won't be able to do full justice to it in 1 hour, but I will try, and I'll try to give you my sense for at least some kind of underlying framework that you can use and hopefully see many echoes of this same kind of thing when you listen to other lectures in the series or later in the workshop. And today, if we have time, what I'll also do is walk you through the entire process, going from beyond standard model physics, or at least one model of beyond standard model physics, through all the stages to at least the experimental level of things where we can start talking about how such a thing is actually measured in the lab. And again, like I said, please feel free to interrupt. Feel free to ask questions if you want me to stop at any point and want me to go over anything you haven't seen. All right, so like I promised, in each lecture, I will say at least one thing that's controversial or opinionated. And in this one, I'm going to state a sort of penchant claim that there's only one thing that we know how to measure very, very precisely. Okay, and we can add one more very there if you really want. So very, very, very precisely, there's only one quantity that we know how to measure. And in fact, you all know the answer to this because you already heard in Professor Rila's lectures in the last couple of days how the new SI system is built up on top of atomic clocks, how pretty much every physical quantity in the SI system now is related in some way to clocks. And so it shouldn't surprise you if I tell you that the one thing that we know how to measure very, very precisely in all of physics is this thing. It's frequency. Okay, and this is an important idea. So let's sort of at least try to understand why. So let's say you have some quantity that varies as a sinusoid. Let's think about some voltage that you measure in the lab. Okay, it's wiggling around. It may change slowly. After a while, it may start speeding up. But whatever it is, it's some kind of oscillating signal. Note the key thing that the thing that we like measuring about oscillating waves is not necessarily that. The amplitude of a wave is not a great thing to measure. Okay. Instead, it's the frequency, or if you like, the number of zero crossings per unit time. That tends to be a more robust quantity to measure. That tends to be a nicer quantity to measure. And it's worth kind of thinking about why this is true, because it's really quite surprising, right? I mean, it's really quite amazing that the entire new SI system bases everything on the measurement of frequency. You want to measure a mass, it's eventually a frequency measurement. You want to measure lengths, it's a frequency measurement. You want to measure current, it's ultimately a frequency measurement. And so why is frequency so special? What's so great about it? And partly the answer is historical. Partly the answer is that in some sense, thanks to atoms and molecules, we've had extremely good ways of measuring frequency. That's a bit of a circular answer. It says we can only measure frequency because that's the only thing we know how to measure very precisely. That's not super satisfactory. So in fact, I myself wasn't quite sure why frequency was so great until I started sort of thinking harder and trying to state it in a way that that hopefully finds some resonance with people in the audience. And the answer, at least my version of the answer, is the following. The reason why frequency is such a great thing to measure, why it's such a robust thing to measure, is because because of the following fact. Okay, the fact is that the world is nonlinear. It's mostly linear. It looks linear enough that we often get fooled and we can get away with the first order approximation to many things. But the world really is quite nonlinear. And so if you have some signal like this that's generated by something interesting in your experiments, by the time you measure it, this will get slightly distorted. Right? So this, if you think of your input, the thing going into your system as something that looks like that, your output will look very slightly different from this exact thing. And what might happen is that you might start to see at some very small level some amount of distortion. Okay, your sine waves will start to get a little bit rounded out. And that tends to play havoc with measurements of amplitudes. Even in a linear world, measuring amplitudes is hard because you have to calibrate your gains. But if there's any nonlinearity at all, then measuring amplitudes is a sort of problematic thing to do. On the other hand, frequencies are great because in the presence of nonlinearity, all that happens is that your input signal, which looks like, for example, sine omega t, tends to turn into, let's say, some bit of sine omega t, that's the linear part, and then a little bit of nonlinearity that leads to a sine squared omega t. But the neat thing is that sine squared of omega t contains frequencies which are integer multiples of sine omega t. And so it's this sort of neat nature of sines and cosines, if you want to put it as a mathematical fact. That means that if you have a frequency, if you have something that's oscillating at a certain frequency, even if it goes through a nonlinear system, you can still recover extremely well what that frequency was that went in. And okay, you might see some harmonics, you might see some multiples of that frequency, but you'll still be able to get that base frequency really well, even in the presence of nonlinearity. Okay, so that's in fact one of the nice things at least about measuring frequencies. But the fact remains that this is the thing we know how to measure. And so, because this is the thing we know how to measure, the basic algorithm for any kind of experiment or idea that wants to measure beyond standard model physics using the tools of atomic and molecular physics is you have to take whatever thing you care about, okay, whatever quantity you care about, and then you have to map it onto a frequency measurement. All right. And what is the frequency? Well, at least quantum mechanically, we know that frequencies basically are the same thing as energy differences. And so really what that means is that you have to think about the beyond standard model physics that you're interested in. And you have to basically think of this as leading to some kind of interesting energy differences. And those energy differences, which result from some kind of interesting BSM physics, are the things which are your basic observables. Okay, and this basic paradigm or this way of thinking about beyond standard model searches sort of captures a lot of them. It's not doesn't capture every single one of them. There are some notable ones which are not frequency measurements; they measure transition amplitudes, but this does encompass a lot of them. And so the way this works is, and we'll see a more detailed example as we go on, but I want to give you a sort of basic sense for it. So the idea is you find some quantum mechanical system, let's say your favorite atom or molecule, and we'll talk about how those get picked, what the right ways to pick them are as well. But you pick your system, and your system is going to have some energy eigenstates. Okay, and you're going to label these eigenstates with the values of energy, other quantum numbers like we talked about. But let's keep it very simple and think about these states as A, B, C, D, etc. What you would like in your system, once you've picked some atomic system where you want to measure BSM physics, is you would like that BSM physics to show up as some kind of measurable energy difference, either the difference between A to B, or B to C, or A to C, and so on. And so you have lots of energy differences to play with when it comes to atoms because you end up with lots of energy levels. But there's another aspect of it which is important. See, BSM physics leads to changes in the Hamiltonian. Okay? And the way it turns into energy differences is because it adds extra terms to the basic Hamiltonian of atoms and molecules. And through that Hamiltonian is how you end up with these energy differences. And so what that means is if your Hamiltonian contains a beyond standard model perturbation or beyond standard model effect, and it moves these levels, let's say we focus on the A and B levels. So let's say A gets pushed down in energy by this beyond standard model physics. And so A turns into something that's a little lower in energy. If B also gets pushed down by the same amount, then measuring this A to B energy difference is rather pointless. You can measure this all day, but if both of them get shifted in the same way due to beyond standard model physics, or really this is true for any other kind of measurement you want to do, if you want to make a magnetometer. So what you really like is you'd like levels which have some kind of differential sensitivity. Okay. Essentially, if one of them gets shifted one way, you want to find another level somewhere in your atom or molecule that gets shifted in the opposite way, so that you can now measure what happens to some energy difference in the presence of the perturbation due to new physics. And then you can, of course, also try to find other combinations, other ways to check whether this energy difference really is coming from new physics. We'll see examples of that. But the essential idea is that you want find states within your system which have a differential sensitivity that leads to an interesting energy level difference, which in turn turns into a frequency that you can go and measure. Is that idea clear? And do people have any questions about this essential idea? Okay. So let's look at an example of what I mean, to see a concrete example. Yesterday, someone mentioned the example of quantum electrodynamics and the lamp shift in hydrogen. So let's take a look at that particular system. So in hydrogen, the ground state is the 1s state, and we'll write a few more quantum numbers. If you've seen these kinds of things, great. If you haven't seen them, don't worry about it. And then what you have is you have a state that's called 2s1/2. And then very close to it, slightly different from it, you have the state 2p sub-half. And this energy difference is the so-called lamp shift. This is the thing that was expected to be zero before quantum electrodynamics. And then people realized that it's actually not zero through experiments. And they discovered that it was non-zero, and that was, that's the kind of origin story of quantum electrodynamics. But if you sort of think about what's actually going on here, measuring this energy level difference, or measuring this frequency between the 2s and 2p half states, which, depending on how you count it, is roughly 1 gigahertz. Measuring this energy difference makes sense because what actually happens because of quantum electrodynamics is that this 2s1/2 state gets perturbed significantly more and significantly differently from the 2p half state. Okay, the intuition is that what's happening with an s state, right? You've got your nucleus, you've got the electrons. With an s state, there's no angular momentum. So the s states are sort of like a satellite that's up in the sky, which suddenly lost its angular momentum. So all it does is it just goes flat. It just goes straight into the nucleus. But of course, it doesn't stop there. It sort of comes out the other side. And so all it's doing is sort of going back and forth through the nucleus. So that's an S state. You might say, wait a second, that looks nothing like my chemistry picture of an S state. It was supposed to be some slightly symmetric ball. And the answer is, well, this is exactly what it does. But of course, you have to add quantum mechanics, which says, well, if you know that there's no angular momentum, you have to have lots of uncertainty in the angle, right? Essentially full uncertainty in the angle. So this is basically what an S state is. It's the electrons who are going straight through the nucleus, but doing this along directions which are completely quantum mechanically spread out, right? Quantum mechanically smeared out, consistent with the uncertainty principle. And so that's all of it. That's why it looks slightly symmetric like you're used to. But the idea is that the electrons going straight through the nucleus and back to the other side. So that's an S state. Meanwhile, in a P state, it has 1 unit of orbital angular momentum, so it behaves a little bit more like what you would think, a planet around the sun does. So if that's your nucleus, that's the electron in a P state. So there is a bit of angular momentum, so this electron avoids the nucleus a little bit. There's an angular momentum barrier to getting too close to the nucleus. This is not completely 100% true because we have to do this all relativistically, but this is a pretty good starting story. And so if you now think about why then the lamp shift is a nice thing to measure, it's because this S electron gets really close to the nucleus. And therefore, it starts going very, very fast. And it also starts seeing bigger and bigger electric fields. So all of the fun quantum electrodynamics effects actually kick in more for these S states. And they're not quite as strong for the P states. And so this lamp shift is a classic example of this kind of differential measurement like I was talking about. You find 2 states within your system, one of which is sensitive in a very different way from the other one. And then you can now go and measure the energy difference or the frequency difference between these states. And that becomes now an interesting observable. Okay, so I'd like to just sort of carry this example if you're looking for a concrete example of what it means for what it means to do this sort of thing in an experiment. Is that okay? Let's pause here for a few seconds just to see if people have any questions.
There are questions, please bring it now. You can also ask questions at the end, but
I can hear that someone's saying something, but it's not super loud. So if you don't mind repeating it again, please.
Amar, that's me. Actually, I'm asking to the students if they have any questions.
Okay. Sorry about that. Yeah.
If no question, no, I don't see any questions at this moment. So Amar, you can proceed.
All right, in that case, I will make the instructor's assumption and assume that no questions means everyone's fabulously following along and everything is crystal clear. I hope that's the case. Okay, so the second sort of thing you can do along these lines is the following. And so what you would also like to do is to measure this frequency very, very, very precisely. So let's say you've got two energy levels that, again, you're trying to measure the energy difference from. By the way, I'm going to use the words energy and frequency interchangeably because to me, those are the same thing, or energy differences. They're the same thing because the modern SI system has finally sort of given reality to something that we were all doing in labs all the time anyway, which is that H bar is just some conversion between joule and a hertz. A joule is a ridiculous amount of energy to be using as a unit when talking about atoms and molecules. A joule is about as much energy as a brick has when you drop it on your foot. And so that's a really macroscopic amount of energy. It has no place in the microscopic world. So we'll just measure energies in units of hertz, et cetera, in frequency units. And I hope that's okay with everyone. So let's say you've got some energy difference or some frequency that you're measuring. And let's call this resonance frequency omega naught. The sort of cartoon experiment for measuring this energy difference is what you do is you shine some light on your atoms with some frequency omega. Notice it doesn't have a subscript, so this is light. And then what you hope is that if you start off all your atoms or most of your atoms in A, you shine some light. And if you happen to hit the right frequency, some of your atoms get promoted into B. And that's what you go and try to measure experimentally. And so what you're always doing is you're tracing out some kind of resonance curve where you're plotting the frequency of the light on one axis, you're plotting on the other axis how many atoms you excited into this state B, which I'll call the probability of being in the excited state. And then if your light frequency matches the resonance frequency omega naught, then you expect to see some sort of resonance. Resonances always have widths. They're only delta functions in textbooks. In the real world, everything has some width. And so the task is going to be to try to measure how, to the best of your abilities, accurately and precisely, what the center frequency is of these resonances. Okay, so we're always going to be worried about, for example, the frequency uncertainty of a measurement. And this should tie in with things you've been already hearing about in other lectures and this school. Okay, so if that's the task ahead of us, this leads to a couple of different things. So you could, of course, try to make delta omega really small in your experiment so that you can get a very good measurement of omega naught. Or you could arrange for your atom to be the kind of system where you get some frequency difference between these two states or energy difference between these two states, omega naught. But then you do something different. You do something where you expose your atom to a magnetic field, and through some coupling to new physics, through some coupling to beyond standard model physics, what that does is it sort of slightly shifts your resonance by some amount. So whether you're looking for shifts of a resonance or whether you're measuring the absolute frequency omega naught, either way, the figure of merit that's important is this frequency uncertainty. I have to emphasize that when I write this down as a frequency uncertainty, and this is what we'll discuss in the next few minutes, I will basically be talking about at least the what in sort of older analyses would have been called the statistical uncertainty. I will mention some aspects about systematic errors as well, but by their very nature, almost, systematic errors are not something which you can open up a book or listen to someone talking about in a lecture and immediately understand. To really debug systematic errors, you have to know your physical system that you're working with inside out. You have to be haunted by it. You have to lose sleep over it. You have to really be close to your experimental apparatus to be able to understand how it's affected by things that could fool you. And so that's the whole world of systematic errors. So mostly we'll pretend as though the errors that matter right now are statistical, but I just wanted to give you a caveat that's only half the story. You can have an experiment which has beautifully small statistical uncertainties, amazingly precise experiment, but if you forget something important, you could be measuring something entirely wrong or irrelevant or both. Okay, cool. All right, so because we're going to be talking about this kind of thing, also known as spectroscopy, let's sort of build up some of the math that's required to understand what's going on. Most of this, again, will be things that you may have seen or will see in other lectures, but I thought it'd be useful to do this a little more systematically. It doesn't hurt to see the stuff again and again if necessary. So let's again think about this A and B system. And if we don't like A's and B's, we can also call this the ground state. We can call this the excited state. So we can talk about the G and E system. Okay, and so that's what I'll do from now on. I'll call these G and E. And so you have your system of two levels. And of course, most atoms are, you're not going to find a textbook two-level system in an atom. You'll only find that if you deal with something like an electron, which only has two internal degrees of freedom. But we are going to isolate or imagine that you can sort of fixate on two levels within an atom, and we'll think about what happens with these two levels. And so we'll assume that at time t equals 0, the population in the ground state, or the probability of being in the ground state is 1, right? All your atoms are in the ground state. And consequently, the probability of being in the excited state is 0. And what we would like is we'd like to understand what happens to the probability of being in the excited state at some later time, starting from this, under the influence of light, under the influence of an experiment where you shine some light on your system. So let's write down an actual Hamiltonian so we can talk about something a little more definite. So what I'll imagine is that the interaction Hamiltonian between the atom and light looks like some atomic operator, A, and then a field operator, F. Okay. You may have seen examples of this. If you have an electric dipole, right, interacting with the electric field of light, then your atom field interaction Hamiltonian, which you normally write down, is minus d times the electric field. I've used E for energy, so I'll use this kind of curly E for electric field. If you want to be fancy, you can also write this as a dot product between some component of D and component of E, and you may have seen this kind of interaction Hamiltonian for the interaction between light and atoms. If you are more familiar with magnetic resonance, you may have seen a similar kind of thing with magnetic moments interacting with magnetic fields. If you're the rare sort of person who works with higher multiple moments, you may have seen other interactions of this form involving quadrupoles and so on. But in all of these, the basic interaction Hamiltonian between light and matter looks like an atomic operator, right? Something to do with matter, like the mu or the d, and a field operator, like the E or the B. So in both cases, it's a sort of atomic operator times field operator. So I'll just use this notation to represent this. And then your field operator, by which I mean the electric field or the magnetic field typically, is going to look like some kind of sinusoidal perturbation. But it's not going to be an infinitely long-lived sinusoidal perturbation. I don't have that much time in my lab. My students need to graduate. I need to do important things like, I don't know, writing grant proposals or something. And so all experiments have sort of finite interaction times between light and matter. So let's imagine you start off your light field doing something interesting at time t equals 0. You make it do something, and then after a while you stop. Okay, and this frequency is what we're calling little omega. And this is the thing we're going to be changing around. And we'll also imagine that there's an overall sort of envelope of these oscillations, which is determined by some envelope function. We'll give it some name further on, but that's the essential idea. You're shining some kind of pulse of light. The exact shape of this pulse, we'll talk about it, and we'll see why it sort of matters and sort of doesn't. But that's the basic idea. You're shining some finite pulse of light with a certain frequency on your atoms, and then you're asking, after interacting with this pulse of light, what is the state of the atoms? You can, of course, for a two-level system, do this analytically and solve it exactly. That's called the so-called Rabi model. But we'll do this using perturbation theory because that's a little more general, and it conveys the idea, and it sort of also leads to a neat little trick, which might be hopefully new to some of you. So what we'll do is we'll try to solve this problem using perturbation theory. You have your ground state that you start off and initially end up through some interaction with light in the excited state. And so just a sort of reminder on perturbation theory, what you're solving is the Schrodinger equation with the appropriate phase factors and things to make your life easy, so that you can only fixate on just the interaction Hamiltonian and you don't have to stress about the full Hamiltonian. That's the basic idea with time-dependent perturbation theory. And so the equations for time-dependent perturbation theory are sort of going to look like I ddt of, for example, the coefficient sitting in front of the wave function. So if you write the wave function of this as CGG plus CEE, then, for example, the C coefficient sitting in front of these basis states are going to satisfy the Schrodinger equation, which turns into a sort of set of differential equations, which is going to look like sum over everybody else of alpha, your interaction Hamiltonian, whatever your other states are, beta, okay, and then e to the I energy of alpha minus energy of beta times C beta T. And there's a sort of telescoping aspect to this, which is that the perturbation or the solution to C alpha to order I plus 1 is related to the coefficients to order I here. We're not even going to do anything fancy here. I'll just stick with first order perturbation theory. And so really what I mean by that is that your first order perturbations can be written down as depending on the zeroth order values for these coefficients. But this is, again, much fancier than it needs to look, because the zeroth order guess for the coefficients is that they don't change. They're whatever their initial values are. And so if you sort of clear away all the muck, what you'll find is that the amplitude to be in the excited state, the first order, is sort of going to look like minus I, the integral of the matrix element between the excited state and the ground state of whatever your interaction Hamiltonian is. Okay, e to the I times the energy difference, and that we've already called omega naught, times the coefficient for the ground state, but that's just CG at to zeroth order, which is just equal to 1. Okay, so this thing is not very useful. We don't care about it. We can also unpack this Hamiltonian a little further, because the interaction Hamiltonian, remember, is the product of an atom operator and a field operator. We can realize that this is a sandwich that only really needs to involve the atomic operator. And then the field lives outside. But this atomic matrix element is, again, also a constant. We also don't even really need to hold on to this inside the integral. But clean things up a little bit. That's all it is. Okay, now for our field quantity, like I said, we are going to assume that this field function looks like a nice sinusoid. But if I write it like that, it means that it goes on forever from minus infinity to infinity. So what I'll do is multiply this by some envelope function. Okay, so this little f of t is going to be the thing that basically determines what is multiplying an infinite sinusoid. So little f of t is going to be whatever this envelope function is. That's the thing that's going to contain information about how long the pulse was, how big the pulse was, all that sort of thing. Okay, so again, if I put that all in and clean up my equations, what I'll find is that this is going to look like the envelope f of t, e to the I omega naught minus omega. And that's all there is to it. Okay. And now, what are the limits of this integral? Well, the limits of this integral I'm going to claim are actually minus infinity to infinity, because all the information about how long the pulse lasted for, I absorbed them into the definition of this envelope f of t. For example, if this is a finite pulse with a rectangular envelope, I can plug that into f of t. But that f of t will decide the region over which this function has support, or the region over which this sinusoid actually is non-zero. And then all the places that are zero, it's okay. We don't even need to stress out about them. They don't contribute to the integral anyway. So I can just write this integral as going from minus infinity to infinity with the sort of additional idea that this contains the envelope, and therefore it also sets the non-zero contributions to the integral. Okay. Let's not even write that. It's probably very obvious to everyone. But the point I want to make is that if you write it down in this form and you stare hard at it, you'll realize that this is starting to look very, very, very much like a Fourier transform. Okay, so basically the excited state amplitude at some time that's well after your pulse has been switched off, which we can call infinity here. This amplitude is nothing but the Fourier transform of the envelope function. Okay, and so I can, with some slight bit of abusive notation, just write this as the Fourier transform of little f from the time domain to the frequency domain, evaluated as equals omega naught minus omega. So if you know what the Fourier transform of your envelope function is, you can actually directly read off or sketch, if you like, the excited state amplitude. And if you care about the population in the excited state at some fairly long time after the pulse is turned off, then this is basically just whatever your atomic matrix element is, times the mod square of your Fourier transform evaluated at the frequency omega naught minus omega. Okay, so it really is that simple. If you know what your envelope is, the Fourier transform of the envelope tells you the line shape of your spectroscopic profile. Let's play with some examples because this will be useful to understand. So if I choose to only light up my atoms with a pulse from the field for some time that looks like tau, say. Okay, so that's my f of t function in the time domain. Well, you all know what it looks like in the frequency domain. In the frequency domain, this is going to look like a sinc function. And if I want to plot the probability of being in the excited state after this pulse as a function of omega, which after all, remember, is exactly what we're doing when we're trying to do spectroscopy. You want the probability of ending up in the excited state as a function of omega. This is just going to be the mod square of the Fourier transform, or in this case, a sinc squared function. And where is the sinc squared function centered? Well, if this was just f of t, the sinc squared would be centered at frequency 0, but you just have to move it over. That's basically what this omega naught minus omega is telling you. You just have to move over that sinc squared function to be sitting or centered at omega naught. Okay, and in fact, this is exactly what you get. This is the excitation profile for a square pulse. You may have seen the solution derived in other ways, but I always find it really remarkable that underneath it all, there's just a very simple Fourier transform relation hiding in there. So if you know your Fourier transforms, or if you can sketch your Fourier transforms, you can get the spectroscopic line shape pretty easily. Okay, so this is not just a matter of convenience. You can also learn some interesting physics from all this. So first of all, what you realize is that this excitation line shape has a width to it, which is determined by the Fourier transform relation. So if this envelope function f in the time domain has a width tau, then in the frequency domain, it's going to have a width that's roughly 2 pi over tau. Okay, there is a small order unity numerical factor in front. You can work it out if you really want. Turns out to be 0.89, but that's close enough to 1. We won't stress about it. The point I want to make is that this width of this feature in the frequency domain goes inversely with the pulse width in the time domain. And so if you have a long pulse, then you get a narrow line shape, you get a narrow profile, or a narrow range of frequencies over which you can excite the atom around its resonance frequency omega naught. And of course, you may realize that this is just a consequence of the energy-time uncertainty relation, or also known as the Fourier transform. But the neat thing about this relation involving Fourier transforms is you can directly also sketch the properties of this excitation profile. And so to do a slightly more non-trivial example, let's look at one more example. So this is an example of what's called the method of separated oscillating fields, separated oscillatory fields sometimes, but often just called the Ramsey method. And again, you can work out the details of the Ramsey method using full-blown algebra, lots of perturbation theory, and so on. But here's the easy way to it. In the Ramsey method, what you do is you light up your atoms with a field pulse that has a profile that doesn't look like one pulse, but in fact looks like 2 pulses. That's it. That's the entirety of it. It's deceptively simple. So the idea is you have pulses which have, again, let's say width tau. And in between these pulses, or if you like, center to center between these pulses, they're separated by a different time scale, which we'll call capital T. And that's it. That's the essence of the Ramsey profile. You're lighting up your atoms with, instead of 1 pulse like we did here, 2 pulses. But with this identification of the excited state probability as just being the same thing as the mod square of the Fourier transform, we can directly draw what the spectroscopic line shape looks like. So the question is, what is then the Fourier transform of something that looks like 2 pulses separated by a distance? Well, we can work it out, because 2 pulses separated by a distance is basically nothing but 1 pulse with tau convolved with a pair of delta functions separated by a distance t. Do you agree? This pulse, double pulse shape is exactly what you get if you have a pair of delta functions, and then you sort of transport your single pulse across both of these and convolve both of them. And so if you realize that the Ramsey pulse shape or the pulse envelope is just a convolution, then your life is super easy, because a convolution in the time domain just looks like a product in the frequency domain. And so in the frequency domain, all we should be doing is looking at a product of this thing, which we already know about, the sinc function, which came from the square pulse, with the Fourier transform of a pair of delta functions. But the Fourier transform of a pair of delta functions is again a very easy thing. If you stare hard at a pair of delta functions, you'll realize that this is nothing but the cosine. Right? The cosine contains a frequency and its opposite frequency, so centered around zero frequency, pair of delta functions is just the same thing as a cosine. Which means that our excitation line shape is going to look like a sinc squared function multiplied by a cosine squared function. So how wide shall we draw these? Well, again, Fourier transforms to the rescue. The width of this feature in the time domain we saw is on the order of 1 over tau. The periodicity, or if you like, even the width of these things in the frequency domain is again going to go as 1 over the time scale of the problem, just on dimensional grounds. So this is 1 over capital T. And so in this Ramsey pulse sequence, capital T is quite a bit longer, right? Quite a bit longer than tau. And therefore, in the frequency domain, 1 over capital T is going to be quite a bit sharper and smaller than 1 over tau. So our sinc squared is the thing that's going to be big and broad. And it's going to be multiplied by cosine squared, which is going to wiggle quite a bit faster. Okay, and so that's the Ramsey line shape. That's what it looks like. Often, if you do a good experiment, it'll look much neater and nicer than looking at drawn. But that's exactly what leads to this Ramsey line shape, which you either have already heard about or you may hear about when you listen to lectures on atomic code. The Ramsey line shape, we can go into those at some point, maybe in the next lecture. But at least for now, I just want you to appreciate that all these sort of spectroscopic things that you may have seen are really just sort of simple consequences of a very simple relation, at least to first order in perturbation theory. Let me pause here for a second and make sure there are no questions.
One. Just a minute.
Yeah.
Can you go back to the previous slide?
Yeah.
Yeah, I have very basic question that atomic energy gaps are discrete quantity by quantum mechanics.
Mm-hmm.
But here when you draw the probability graph with frequency, it
Yep.
seems to be a continuous graph where even where you are off frequency from omega naught, you are able to excite the atom with some small probability. Mathematically, I'm seeing how it is coming, but do you have any intuitive answer why that is happening?
You're worried about energy not being conserved?
Sorry?
You're worried about energy not being conserved?
But why
It seems like it, right? Seems like energy is not conserved, doesn't it?
Yeah.
Okay. The short answer to that is in quantum mechanics, you don't have to conserve energy. That may sound crazy and controversial, but it's true. Because, how do you know whether you've conserved energy or not? You have to actually do the accounting. But quantum mechanics says, well, if you've only got some amount of time, tau, during which to check your accounting, so that's what you're doing when you're exciting the atom with the field, is you're transferring energy from the atom to the field, or field to the atom. And so if you only have a time tau to do your accounting, how are you ever going to get your accounting to work out to a higher level of precision than 1 over tau? Or h bar over tau, if you want to think in energy units. Okay, so the short answer is that in quantum mechanics, conservation laws are a lot more flexible than you think. To get exact energy conservation, you actually, in fact, need to interact for an infinite amount of time. For any finite time interaction, energy conservation does not need to be exact. For any finite length scale interaction, momentum conservation does not need to be exact. There is, if you like, quantum mechanical uncertainty that's involved. That's the whole point of the uncertainty principle, is that there's sort of this fuzziness, if you like, in how exactly you have to worry about continuous conservation lengths. Okay, so that takes a little while to get used to, but it's true. And so that's what you're seeing here. Okay, so the math is not lying. What's slightly maybe uncalibrated is your intuition, which is classical. Everyone's always told you energy is exactly conserved, but the point is in quantum mechanics, no, it doesn't have to.
I see.
Great. It's a good question. Thanks. Any other questions?
Yeah, there is one more.
I just wanted to ask that these functions that we have got for the probability looks like single slit and double slit kind of thing. What is this? First one is a sinc square and second one is a cos inside the sinc square. So is it related?
It's a cosine
somehow?
squared again. It's a cosine squared inside the sinc square.
Yes, sir. So is it related somehow or it's just a coincidence?
These are very different functions. Remember, this is a sinc, not a sine. And this cosine squared is coming from the pair of delta functions, if you like. So it's, I guess you could call it, I don't know, just a mathematical fact, if you like. Or, but you're worried about the coincidence that one is somehow related to a sine and the other one's also related to a sine. Is that roughly what your question is?
No, I'm saying double slit, in a double slit experiment.
It's a double slit experiment, exactly. So this is just a double slit experiment because, again, think about the math behind it. Right? In classical optics, you learn that the Fraunhofer diffraction pattern for really any shape of aperture is nothing but the Fourier transform of the aperture.
Yes.
And so that's all it is. So you're just recognizing that in one case, it's a Fourier transform. Well, it's in another case, it's also a Fourier transform. And yes, this exactly looks like the Fraunhofer diffraction pattern for a double slit. And that's again, it's just, you're seeing that there's a Fourier transform at work. The difference is that in one case, it's a Fourier transform from time to frequency. In the case of diffraction, it's a Fourier transform from two dimensions in X and Y in the transverse plane to the propagation of your light to transverse momentum. So that's a Fourier transform in optics that you are seeing from position to momentum. This is a Fourier transform from time to energy, but otherwise, in both cases, it's a Fourier transform. Does that help?
Yes. Thank you.
Okay. Good. Any other questions? Anything else?
Yeah,
we should,
one more. Just a minute.
Yeah. Go ahead.
Hello.
Yeah.
Hello. So in the whole treatment, we are assuming that we know the interaction of atoms with the light very well, right? So what if
You're assuming that you know what the interaction is on. Correct.
so
Yeah.
what if there is a new sector in this interaction? So my question
Okay.
is,
So
how do you know between there is an interaction induced new physics and there is some physics due to that BSM?
yes, so that is another way to look for new physics, as I said. So right now we're sticking to this idea that the BSM physics comes in to an energy level shift. That's the sort of new stuff. And your task as an experimentalist is to try to do the experiment to measure that energy shift as accurately as possible. And that's what we're talking about, right? So right now we're assuming that whatever the interaction is between the atom and light, that's a completely understood standard model, familiar sort of dipole with electric field or magnetic dipole with magnetic field sort of interaction. So we're not putting any new physics into the atom field interaction, but that doesn't mean that you cannot. And so in the next lecture, we'll see an example of how people are looking for dark matter And there, that's entirely the idea, is that you're going to look for new physics to lead to transitions where none used to be. Okay, and so that's a different paradigm for looking for new physics than this thing that we're talking about right now, which is just energy shifts. But I just wanted to sort of focus on energy shifts so we have something to begin with, because this again encompasses quite a lot of measurements, and you'll hear about them during this school as well as the workshop. You'll hear about atomic clocks, you'll hear about magnetometers. It's all basically the same idea.
Okay, thank you.
Yep. All right, great. So let's move on from this and sort of talk about why this is good. So I think we can put a check next to this thing that says, okay, we know how to measure frequencies. We're not quite there yet, because I would actually like to talk a bit about the precision or the uncertainty of these measurements. And so let's do that discussion now as well. So this is great. We have an expression now for the sort of line shape you can get with various different techniques, but let's keep it simple. Let's just talk about the simple single pulse excitation that leads to the sinc squared. This is often also called the Rabi line shape or the Rabi profile compared to the Ramsey profile. Okay, so let's clear up some space so that I can talk about the uncertainty of measurements. This will be a very lowbrow and sort of a experimentalist version of some of the things that you already heard about in many lectures already, and almost certainly was also discussed by Professor Caves in one or more of his lectures. So we're going to talk about how precisely, at least statistically, you can measure a resonance. Okay, so let's say using your favorite method, Rabi, Ramsey, something else named after yourself, you measured some kind of resonance in an atom or a molecule. And so now the question is, how precisely can you determine the center of this resonance? The answer has to do with two things. It has to do with the width of this resonance, which I'll call in general gamma. And it has to do with the fact that, at least in my misspent life, every single resonance I've measured never looks like this. It looks like that. It has noise on top of it. That noise could be, beautiful quantum noise, which is again something you'll hear about in some of the lectures in this school. Or it could be boring classical noise. It could be instrumental noise. It could be the jerk in the lab next to mine who has some instrument running that's broadcasting all sorts of noise. Okay, so we won't worry too much about whether this noise is deeply fundamental, quantum mechanical, or whether it's just some ugly instrumental artifact. But suffice it to say that there's always some noise in the problem. And so in the presence of some amount of noise, and if you have a profile with some width gamma, how well can you identify the center of a resonance? And so I want to build this up intuitively first. And so what I want you to do is think about two resonances. Okay, you measured a resonance that looks like this. Person A. The person sitting next to you, your neighbor, measured a resonance using a different technique. And then it turns out that they have also the same amount of noise that you have. But because they used either a shorter pulse or a shorter interaction time between the field and atoms for some reason, what they got was a resonance which was much wider. But again, with, let's say, at least pictorially, the same amount of noise as you did. If you think about these two just intuitively and ask yourself, which of these two do you think is going to lead to a sharper measurement of the center frequency, of the resonance frequency? Which one's going to give you a more precise measurement of the center frequency? I think you'll all agree that this looks about right. Yeah, so it's sharper. So given all else being equal, the noise being about the same, the signal height being about the same, this one is a nicer thing to measure. And that's true. Your uncertainty in the frequency measurement is going to be dependent on this line width, on the gamma. The smaller gamma is, the smaller the uncertainty is you're going to get. Let's do another sort of intuitive experiment. Let's now assume that your friend has become wiser and they say, oh, well, your technique was better because you measured a narrower feature. I want to use that too. But somehow your friend ended up building a nicer experiment, took better care of their amplifiers. Whatever they did, they ended up with a profile that looked like that. It has some noise, but let's say that your friend is very good at controlling the noise in their experiments, and the noise is much, much smaller visually. So again, if I asked you between these two things, one where the noise was much larger, other where the noise was much smaller, all else being equal, again, your signal height is the same. If your width is the same, then again, I think you'll agree that in this case, if it's a competition between these two sorts of resonances, this one is much better. The one with lower noise is much better, all else being equal. Okay. So again, on dimensional grounds, we can sort of play with this and see how far we get. So this is a frequency uncertainty. Gamma is also something with dimensions of frequency. So this equation is all right dimensionally. But we have the sense that something with a lower noise, lower amount of noise in a given measurement should lead to a sharper estimate, should lead to a more precise estimate of the resonance frequency. Okay. We'll even call this delta omega naught because we're talking about measuring resonance frequency omega naught. And so if you think about this and you play with this, and if you really want, I can give you, again, a sort of simple experimentalist version of how you get this answer. But I encourage you to all try to play with this on your own. This is, after all, a workshop on measurement precision. So you'll see this relation lots and lots and lots of times. You'll see this probably discussed by multiple lectures in the series. And so I want you to sort of take this home with you, play with it during your lunch break or at home, and then see if you can figure out why this has to be true. And then if you have any interesting ways of thinking about it, we can talk about it in lecture 3. But I'll leave you with the answer, which is that this uncertainty scales as the ratio of the signal size to the amount of noise. Really, what it scales with is the amount of noise not far away from the center of the resonance like I've drawn, but the most important place where the noise matters turns out to be there. Okay, sort of the half-height points of this resonance. So in those spots, whatever the noise is, that's what we're calling N here. So this thing is the so-called SNR, or signal-to-noise ratio. And so the better your SNR, the better your signal-to-noise ratio, the better your frequency uncertainty. And this relation is so widespread that you'll see it, whether you're talking about optical interferometers, you'll see it in atom interferometers, you'll see it in clocks, you'll see it in magnetometers. It's just all ever prevalent. Okay, so anytime you're measuring some kind of resonance or some kind of peaked thing which has a certain width and a certain amount of signal to noise, you'll always see this happen. Okay, so then what are your ingredients for making a precise measurement? Let's say you're looking for new physics and you'd like to measure this resonance frequency extremely precisely and accurately. What do you need to do? Well, you need to make sure that gamma is as small as possible. And you also need to arrange for your signal to noise ratio to be as large as possible. And that's essentially it. Okay, there's one more factor to it, which is picking the right kind of system. But once you pick the system, your task is to make gamma as small as possible and your signal to noise ratio as large as possible. If you think back to this sort of analysis that we did, you'll realize that making gamma small is the same as making the interaction time between the field and the atom as large as possible. That interaction time between the field and atom is often called the coherence time. That coherence time can be limited because of lots of different reasons. It could be limited because you came in and then you lost patience, or you only had a certain amount of time to work with your system. So you decided to truncate the interaction between light and the atom to some amount of time. So that could be your doing. Or it could be the fact that, no, in fact, what you did, at least what you thought you did, was you had the field on for a very long time. However, you forgot that you were dealing with atoms, which are like little children, in that they don't stay in one place too long unless you do something drastic to them. And so you thought you were shining light on your atom, but your atom did what atoms do if you don't control them, which is it ran away. It escaped from your measurement region. And so it only happened to interact with your laser beam that you were shining light on the atom with for some finite amount of time. So even though you had your laser on for a long time, the amount of time for which the atom actually interacted with the laser was much shorter. And that can also limit your coherence time. Therefore, that can also lead to broadening. And because this has to do with the atoms flying away, this is often called time of flight broadening. Okay. You can also get broadening from other sort of stranger sources, which is that you think your laser's on for a long time. And you're also certain that your atoms haven't run away for a long time. And yet you'll find that if you do spectroscopy, that you end up with resonance curves that look like they have some kind of width. And that's another interesting fact. It has to do with the following thing. In this entire discussion, remember, we were talking about the amplitude. So the quantum mechanical amplitude to be in the excited state depends linearly on the pulse envelope, on the fields. And so if the fields, even though they might be on for a long time, lose phase, if they lose phase coherence, if they jump cycles, if they skip cycles every once in a while, then the phase of your quantum mechanical wave function also gets reset, also skips. Okay, and if the phase of your quantum mechanical wave function skips, it doesn't coherently add or doesn't coherently accumulate with all the phase that came before it. Okay, so even though it may seem like you have a longer interaction time, in fact, this coherence time should really be the phase coherence time. So it's a measure of how long the atomic wave function phase coherently evolved in sync with the field's phase. Okay, and so in some sense, this thing up in the exponential sort of encapsulates this essential idea that you need the atom and the phase to sort of be the atom and the field to be evolving together in phase with each other. Okay, so there can be many reasons why lines get broadened, but as an experimentalist, your task is going to be to try to make the space coherence time as long as possible. And so if you've ever wondered why atomic physicists spend so much time trying to cool their atoms, what's so great about cooling an atom? Well, the reason to cool atoms is because if you cool them, you slow them. And if you trap them, you can hold on to them. So all this business of laser cooling and trapping, ion trapping, etc., all of that is an aid of trying to make gamma as small as possible, to reduce the amount of motion of your atoms to as small as possible, so that the phase of the atoms keeps track with the electromagnetic field for a long time, and so that you get a long interaction time between the atoms and the field. Is that idea clear? That if you want to do a good measurement, what you'd like is to make gamma as small as possible and signal to noise as large as possible. Any questions about this?
One. Sir, can you differentiate between the classical and quantum noise? I don't understand it. What is quantum noise?
What is quantum noise? I think you have an entire lecture or two scheduled on that later in the school. So ask me on Friday if that hasn't already been covered. How about that? But briefly though, quantum noise, no, I don't even want to tell you the brief answer. Wait for it to be done properly in one of the lectures in the school. But for now, operationally, we're not worried too much about what the noise is. It's something that leads to some fluctuation in the measured populations in the excited state.
Okay, sir, thank you.
All right, in that case, let's move on to the next
excuse
idea.
me,
So, yeah, go on.
So how does the line width of the laser
Mm.
and the excited state line width plays the
Mhm.
role in determining this gamma?
Both of them will determine gamma, and usually it's the one that's worse which dominates. Because again, your laser line width is a measure for how long your electric field in your laser oscillates in a phase coherent manner, just left to itself. Okay, so laser line width is just a measure of how long your laser is phase coherent for. The excited state lifetime, if you have spontaneous decay, or in fact, in other systems, there can be other reasons why the excited state has a lifetime as well, in addition to spontaneous decay. But basically, that excited state lifetime, or what you call the atomic line width, again, is a measure of the duration for which this excited state wave function evolves coherently without skipping phase, okay, before getting reset by spontaneous emission. And so that idea is exactly what we just discussed. It's all about phase coherence time. And if your phase coherence time is limited by the properties of your atom, well, then the line width that you measure will be basically equal to your atomic line width, which is going to be the excited state line width, as you call it. Okay. Instead, if the atom has long phase coherence because you've trapped it nicely, you're holding onto it nicely, it's protected from other perturbations, and it has a very long excited state lifetime. So then you may be limited by the laser line width. And then if you make a measurement of the atomic spectrum, if you had a much better laser, you would have measured a much sharper line. But instead, because you have a laser which doesn't have great coherence time, what you measured is a broader line. Okay, so which of these things dominates depends on which one figure. In fact, if you want to do this all properly and mathematically, then it's going to be determined by the sum of both these line widths. Okay, but again, in practice, either your atoms will be better than your laser, or your laser will be better than your atoms, and you'll spend most of your life trying to fix the one that's not quite as good as the other. Is that okay?
Yeah, Amar, you may go ahead.
Okay, thank you. Okay, so I think we can again put a check next to this and say that, okay, we understand something now about how to measure frequencies precisely. So let's, in the time we have, at least start the next process, which is looking at an example of how you turn something that's an actual high energy phenomenon, a beyond standard model physics phenomenon, into something that you actually measure in. And so the point I want to make is that there are many layers to this. And at each layer that you have to kind of count on people who know what they're doing. So you have to have lots of friends. You can't do this by yourself. Okay. So the first friend you're going to involve is going to be your super high energy theory friend. Okay. So the person who says, okay, let's call them an ultra high energy friend. So the ultra high energy friend is going to say, hey, I have some theory of what might be, the dark matter particles, or what might be some, new particle that's messing with standard model particles, that's interacting in some weak way with standard model particles. And so the example I want to take is the following. So your friend says, okay, I have some crazy new particle which has some very high mass. So I'm going to try to tell you what this particle does. So I have a particle whose mass, which is we can call X, which has some mass mx. And what this particle does is it affects the properties of plain old electrons. So if you've learned a little bit of quantum electrodynamics, this might make sense. If it doesn't, don't worry about it. Just think of it as a story. But in quantum electrodynamics, you realize that if you have electrons, they interact with light. And the standard building block of quantum electrodynamics is this sort of three-point vertex between charged particles and light. So your friend says, hey, look, I can draw a diagram like this, but I can also draw a diagram that looks a bit like this, in the sense that there's an electron coming in, something coming out, and then light involved. But I'm going to fill this thing with a more complicated set of processes. And because this is an ultra high energy friend, here he or she described this using the language of Feynman diagrams. What they say is, I'm going to draw a diagram that sort of looks like that, involving a loop containing my X particle. The X particle then is going to give off or interact with a Higgs boson, which connects to your electron. And the electron also interacts with another particle that's thrown off by an X particle, which happens to be a photon. Okay, so this is an example of an actual Feynman diagram that results in measurable properties, which is the sort of thing people look for. But again, if you sort of stare at this and if you kind of zoom out from this, you'll see that it looks a bit like the three-point vertex. And so what this process does is it sort of modifies the electron-proton interactions. In a less highbrow way, it means that it leads to a measurable electromagnetic moment of electrons, which allows it to interact with light, but in a slightly stranger way than is true with just plain old standard model quantum electrodynamics. Okay, so this X particle is the new thing. Cool. So that's your high energy theory friend, and you say, okay, but excuse me, I'm just a humble experimentalist. This all sounds beautiful and amazing, but how do I measure it? So your ultra high energy friend says, well, your friend might not, but certainly my ultra high energy friend says, oh, okay, I don't have the patience to explain this to you. Why don't you talk to my neighbor who is an expert in translating what I just said into language that you can understand? And so those are the people who work with something called effective field theory. So an effective field theory person says, okay, you know what? I think I understand what this ultra high energy person said. And like we just talked about, it looks like basically you get some kind of interaction between electrons and photons. And so I can actually explain this to you with a little more algebra. I'll tell you that what this effect leads to is an extra piece in the Lagrangian, which I'll call L nu physics. And L nu physics is going to be some coupling constant G, okay? And then what it's going to look like, because of the shape of this vertex that we have, because it's still a photon, electron, electron interaction, just with extra stuff in the middle. And so because of that, it still looks like an F mu nu to do with the field, interacting with a psi bar something psi with some of the moments of the electron. And because this is a mu nu here, to make all the tensors happy, this has to be a sigma mu nu. And then because of the way that we would like this interaction to sort of lead to interesting breaking of the symmetry, this turns out to be coupled to not F mu nu, but it's dual, it's called F tilde mu nu. And then your effective field theory friend says, okay, this is basically like what it is. It should remind you of the plain old interaction between the electron spin and the magnetic field. Except this it's not quite complete because it's not quite dimensionally correct. They'll say, okay, an F mu nu, at least in quantum field theory language, has mass dimension or momentum dimension 2. Psi bar and psi both have mass dimension 3/2. And so this entire operator involving F mu nu, psi bar, and psi, the sigma and the G are dimensionless. So the F mu nu, psi bar, and psi end up giving you something that's a dimension 5 operator. And that's usually a bad thing because it means that it's non-renormalizable, etc. But this is effective field theory. So your effective field theory friend says, don't worry about it. It may not look renormalizable, but basically it's fine. But to make the dimensions come out right, we have to divide this by some mass scale. What mass scales do you have to play with? Well, you have the mass of this particle X that you're working with. And so you could naively just do that. Okay. But it turns out you can also be a little more conservative because it's a two-loop process. What you'll find is that this has to be multiplied by something that looks like the electron mass divided by the mass of this unknown X particle squared. And now this is all happy because mass over mass squared is an inverse mass. This has dimension 5 from the operators, inverse mass dimension. So this is ultimately now a nice dimension 4 operator that you can add to your standard model Lagrangian. And this is the contribution of the new physics. So you say, okay, thank you, effective field theory friend. I understood about 10% of that. If only I had paid attention in my quantum field theory courses instead of playing in the lab and doing experiments, but that's okay. I think I sort of kind of get it. So then your effective field theory friend says, okay, you know what, if you don't understand this, why don't you talk to my neighbor, who's now an atomic theory person. Maybe they can translate it into some kind of language that you can understand, and then you can go back to your lab and measure it. So your atomic theory friend says, hey, look, okay, I think I know exactly what what the neighbors just said, what the effective field theory person just said, but we don't even need to be this sophisticated. What we'll do is we'll basically, average all this over all the crazy high degrees of freedom, and think of the expectation value, if you like, of all this sort of new physics stuff. The effective field theory is already a little bit of an expectation value over the degrees of freedom, which you're not directly tracking. So let's continue that process. And so then you can, in fact, think of this in a much simpler form. You can think of it as a Hamiltonian due to new physics. And you say, aha, finally, language which I can understand, Hamiltonians, energies, great. And so the resulting Hamiltonian for new physics, you can now write down, as it turns out, you can write this down as a quantity which we'll call d sub e. I'll tell you what this is. And then we can write this down as a bunch of familiar operators. If this was a magnetic moment, magnetic field interaction, you would write this as the interaction of the electron spin with the magnetic field. But since this is not a magnetic moment, magnetic field interaction, because of this tilde, which is the dual to the F mu mu tensor, this is actually a spin interacting with the electric field of light, not the magnetic field. And then if you do the conversion properly from the effective field theory Lagrangian, which involves the sigma mu nu, into sort of atomic theory language, you have to write down this beta matrix, which is one of the Dirac matrices. It's the same thing as what would be called the gamma zero matrix by the quantum field theorists, but we'll call it beta for the atomic theorists. And then your atomic theorist friend says, hey, look, this should remind you of something simpler, which is something that looks like the magnetic moment, some magneton times the spin dot magnetic field. And so the spin is, the sigma is just the spin. But because your atomic theory friend works with relativistic atomic physics, they give this to you in terms of the relativistic spin operator. That's why it's the big sigma. But you say, okay, look, I kind of sort of get it. This reminds me of the magnetic moment with magnetic field interaction. This is just a similar thing where the spin seems to interact with the electric field. And you say, do I understand that right? Is that what's going on? Your friend says, yep, that's basically all there is. You just have to be careful. This is relativistic, but otherwise that's the basic story. Are people following along so far? You sort of see at least the steps in this journey. This new thing, or this parameter, which your atomic theory friend introduced by staring at this effective field theory Lagrangian, this is now a quantity with the dimensions of energy per unit length. Because remember, this entire thing is a Hamiltonian. Beta is a dimensionless matrix. Sigma is a dimensionless spin operator. There's an electric field here, and then this whole thing is an energy. So dE has units of energy per electric field. You know from regular ODNM that the interaction energy of a dipole in an electric field looks like the dipole moment times the electric field. Therefore, energy per electric field is really nothing but a dipole moment or electric dipole moment. And so this entire story is nothing but the famous electric dipole moment of the electron, or the infamous electric dipole moment of the electron, which many have looked for and no one has found yet. Okay, but that's the basic story, at least until the level of atomic theory. So then you tell your atomic theory friend, okay, great, this all looks great, but I don't know how to deal with betas and sigmas and all that stuff in the lab. Can you give me kind of a simple experimentalist first? If I go and look for the interaction of a spin with electric fields in the lab, how much of an energy shift should I expect? So then your atomic theory friend says, oh, okay, that's not an answer I can give you in 10 seconds. I need to do some thinking. And so what they do is they go and look at their favorite periodic table. Okay, they'll go look at their favorite periodic table and they say, okay, which of these things do you want to work with? And as an experimentalist, I say, well, I don't know. Why don't you tell me which one's the best one? Because I'm happy to do experiments on all of them, as long as I can get my hands on them. Okay, maybe I don't really want to do experiments with these things out here. They're impossible to get. You have to bribe someone. You have to work at some crazy labs to get them. So let's maybe leave those out. But that's still okay. Just tell me which ones work best, and I will go and figure out how to do the experiment with them. So your atomic theory friends go and work hard, and they crank the knob, and they take this basic relativistic Hamiltonian, and they go and calculate what its expectation value is in each of the atoms. Because remember, this is written in terms of operators to do with the bare electron. Well, not quite the bare electron, the renormalized electron, but it has to do with individual electrons. Whereas we're not working with individual electrons, we're working with atoms. And so your friend goes and tries to find out what is the expectation value of this H nu physics in whichever atom that they go and make their calculations in. That's not an easy process. Again, you'll have a lecture about it, I'm sure, about whatever's involved in doing these calculations. Takes a lot of effort, a lot of thinking, lots of computer time. But at the end, they can go and calculate this for you. And they say, hey, look, I'll tell you what the answer is. The answer is that you will get some energy shift, which I'm going to call W. We can even call it WEBM. And this thing is going to be the amount of energy shift that you get. So this has dimensions of energy. It's the expectation value of the Hamiltonian. But not just that. Remember, this operator that the atomic theorists started working with involves the spin and it involves the electric field. So some of that still survives. They say, okay, look, and then the energy shift that you get depends on which way the spin is pointing relative to the direction of the electric field. Okay, and they tell you, okay, I can go and calculate what this W quantity is, and I can tell you the answer for a whole bunch of different atoms. The easy ones to calculate this for are the ones which have one valence electron, because you can sort of pretend that the rest of the atom doesn't contribute too much. That's a rough approximation. People started doing that in the 60s and 70s, and actually Salpeter did that in the 50s as well, 1950s. But you can now, with modern techniques, start doing them for more atoms which are sort of deeper inside the periodic table as well. And I'll let my atomic theory expert friends comment on exactly which ones are easy, which ones are hard, etc. But they tell you, okay, look, this is the Hamiltonian that you need to work with. Or in other words, this is how I can parameterize what the energy shift is due to new physics. Okay, so this is actually going to be our starting point, which is we're going to pretend that this is actually the interaction Hamiltonian between the atom and the field due to new physics. And this is going to be some quantity, which you have to rely on your buddies to calculate for you, times the spin of the atom, or the net angular momentum of the atom, times the direction of the electric field that you go and apply in the lab. And so next time we'll start talking about how you actually turn this thing into a measurement. And that'll be the rest of the story. Okay, so I'll stop here because we're over time, but I'm happy to answer questions if people want to ask questions.
Yeah, thank you, Amar.
My pleasure.
So there are questions.
Yeah.
Hello, sir.
Mhm.
So, sir, if we look in the Rabi profile, so we
Mhm.
are applying a pulse of or a step function for tau time.
Yeah.
And when we are
Yeah.
looking at the probability, we saw some kind of sync function, which
Mhm.
means like the probability once becomes 0, then again the height is changing. So, sir,
Yeah.
is there any physical reason that this kind of profile we are seeing?
This is all physics, right? All of this is a physical reason. You want some story for why this is 0 or why this became 0 at some points? Is that sort of what you're asking
Also,
for?
the why height is varying.
Why the height's varying? Okay.
Yes, at omega naught is looks like maximum, then it's decreasing also.
Okay. So before we get into intuition, let's at least make sure the math is solid. So do you at least follow the math here? You agree that this is what you get based on quantum mechanics, based on simple Fourier transforms, etc. I hope you're at least convinced of that. The idea for why the probability of for excitation is, first of all, not very large when you go off resonance. And not only that, it has these sort of conspicuous sort of minima at certain frequencies as well. It all has to do with interference. Okay, so let's think about this integral. And let's think about this integral like babies, okay? In other words, if I have an integral that looks like dt f of t e to the I omega naught minus omega t. This integral basically means I'm actually looking at f of t times omega minus omega naught t for times t sub I. I'm adding up all the contributions for different t sub i's together, and that's basically what this integral is. Okay. And so what is this integral telling you? It's telling you the probability amplitude to be in the excited state. So what this integral is measuring for you is what is the quantum amplitude to go from the ground state to the excited state due to something that you did at some time t sub I. And so what you're doing is you're adding up for time t1, what was the amplitude? For time t2, what was the amplitude? For time t3, what was the amplitude? But you're not adding the probabilities, you're adding the amplitudes. And so what can happen is that the amplitude for excitation at some time t3 can have a different phase than the amplitude for excitation at some time t1. Why can it have a different phase? Well, obviously, because there's a phase factor sitting in here. And that phase factor depends on how far off resonance you are. If you're exactly on resonance, if omega naught equals to omega, then all the quantum amplitudes for excitation at different times all add together with the same phase, because this phase factor that sort of changes from T1 to T2 to T3 is 0. One of those. The phase is 0, so its factor is 1, and therefore all these quantum amplitudes add with the same phase. But if you go off resonance, these quantum amplitudes will add with different phases depending on when in the excitation they happen. So an excitation due to this chunk of time may add constructively with an excitation at some later amount of time if the phases end up being favorable, or it may add destructively for the excitation at some other amount of time. And so you see what this is. This is a massive interferometer or an interference experiment. You start off your atom in the ground state, you send in light that may seem like a long pulse, but you should really think of that long pulse as being lots of little pulses, lots of short pulses. And what you're measuring at the end is what the total excitation was, but you're not really asking how much was because of pulse 1, how much was because of pulse 2, how much because of 3, how much because of 4. You're asking for what happens because of the aggregate. Okay, so it's a kind of classic quantum interference kind of story. So you're exciting with many, many possible pathways, and then you're looking in the end for what the probability is due to all of the different pathways adding their amplitudes together, either constructively, destructively, etc. So there's a lot of sort of interesting physics hidden in this very simple idea that this is equal to the integral of the field function. Does this give you some insight? So that's exactly why you see these sort of dips. That's also why you see the peaks and dips and so on. It's just a manifestation of interference for the excitation of the atom due to light at various different times, all adding in amplitude. And then you add them and then use mod square, and then you get the probability. Does that make sense?
Thank you, sir.
Hi, sir. Suppose if we are measuring the atomic line width and you're using a laser with a bit bigger line width than that, so can we use deconvolution to get the actual atomic line width? I mean,
you can infer it, but unless you know what the phase fluctuations of your laser were, you cannot undo it.
But you can get
what I mean by that is the following. So what I mean by that is the following. Let's do a rough numerical example, and then you can tell me the rest of your question. So let's say you know through other measurements that your laser line width is, let's say, 10 megahertz. You go do spectroscopy of some atomic transition, and you find a width that's equal to, let's say, 14 megahertz. And so then you say, wait a second, my laser was 10 megahertz wide. This profile seems to be 14 megahertz wide. Where did the remaining 4 megahertz come from? As long as your laser itself didn't get worse without you noticing it, it probably came from the atoms. Okay, so that's the sense in which you can sort of deconvolve what's going on. But can you figure out exactly what the atomic line shape is by deconvolution? You can, but as you know, deconvolution is tricky.
Yeah.
And the reason it's tricky is because of the following thing. And it kind of comes down to this. So the stories are sort of all here, right? So what's happening is to calculate the excitation amplitude, you're basically multiplying the field operator or the field function, or the field envelope function with whatever the atomic matrix element is. Okay. And so that convolution is happening in the amplitudes. Whereas what you measure are the probabilities or the mod squares of the amplitudes. And so it's the same problem as in optics, right? It's like saying, you know, you are trying to resolve a star. It looks blurry, doesn't look like a sharp point. The reason it looks blurry is because there's some instrumental response of your telescope, which gives you some point spread function. But in addition to that, the star itself might have some interesting structure, it might be blowing off some gas, and so it might also have some contributions. But if you want to know exactly how big the actual star is in the presence of some amount of blurring because of your telescope, you have to deconvolve it, but it's hard because you have the convolution happened in the fields, and what you're measuring is the mod square of the field. So in measuring the mod square, you've already thrown away information about the phases.
Okay.
So that's why deconvolution is hard. Does that make sense? So it's the same story.
Yeah, I got it. What is basically the limit? I mean, how small does the laser line width have to be compared to the atomic line width? Can you, I mean, is there some sense to that?
It's just a question of what you're willing to work with. So again, you'll hear lectures about atomic clocks. You'll hear about people who are working with atoms whose line widths, say, are about 1 hertz. So if you're trying to measure an atomic transition with a line width of a hertz, it's nice to have a laser whose line width is much smaller than a hertz, so you can be dominated by the atoms.
Got it.
But then there are also other people working with atomic transitions whose line widths are 10 to the minus 9 hertz and nanohertz or so. At that point, right now, we have no way of making lasers with those kinds of very narrow line widths. So at that point, you're always limited by your laser line width. Okay, so it really depends on the details of what the system is that you're trying to measure, how good your light source is, and all that sort of fun stuff.
Yep. Thanks.
maybe a naive question, but how far can you go with maximizing the SNR? Like you can in principle increase the number of emitters and you're always limited by noise with the experimental devices, but is there kind of a fundamental limit on how high you can go?
That is a fantastic question. And I, again, strongly encourage you to ask that to the speaker at some point later today, I believe. Someone's going to talk about that exact question. And the answer is yes, there are fundamental limits. So you're right. If you want to make your signal stand out above instrumental noise, one way to do this is just get a big heap of atoms. You get more and more and more atoms, and you get so many atoms that your signal from your atoms, and in fact, the noise from your atoms, which is the quantum noise that's unavoidable, that overwhelms all of the boring instrumental noise. That's the dream, okay? Is you work with such a beautiful ensemble of atoms so that their intrinsic noise, their unavoidable quantum noise dominates over everything to do with all of the classical boring measurement devices. So you can certainly get to those kinds of regimes. Usually the opposite way, by working really hard and making good amplifiers, good detectors, thinking about isolating your system well, so that you make your instrumental technical noise much smaller than the more fundamental quantum noise. But what is the fundamental limit to the quantum noise? Well, that's again, like I said, a fun question, which I encourage you to ask. I believe Saikat Ghosh is talking about some of this kind of stuff later today or tomorrow or something like that, right? So ask him, and if you still have residual questions, or in fact,
Tomorrow
using
he'll be
what you
talking.
learned, perfect. Yeah. So based on what you learned from that, you can come back and we can carry the discussion forward. Yeah, but that is a very good question, and in fact, there is a good answer for it as well. How to achieve that limit? How you build experiments that really are truly dominated by the quantum limit? That's an active field of research and study.
Yeah. Any more questions, comments? No. So if not, let's thank Amar for this beautiful talk.
Thank you very much, and I'll see you on
Thanks,
Friday.
Amar, for sparing us, with us at odd times.
Oh, that's all right. It is in fact an odd hour. It is 1 a.m. in the morning, but it's been a very enjoyable thing to speak to you. I hope
would have been very happy if you were here. Okay. So
Yeah.
many
See you
thanks.
on
So
Friday.
now
Bye.
we'll have a break for the